Okay, so today my topic is Spin Orbit Torque MRAM. First, I would like to introduce some background knowledge. Our RAM is one of the core components in modern computers, and nowadays the demand for much smaller, faster, and ultra-low power system keeps growing. Researchers are focused on improving the performance of integral circuits and lowering the energy consumption of embedded memories. So a possible solution for this is to use magnetoresistive random access memory, which is MRAM. It's a type of non-volatile random access memory. So instead of using charge or current flow, it relies on magnetic elements to store information. So MRAM have a relatively higher reading and writing speed than SRAM in large scale. It also has an advantage of DRAM, which is a relatively high density. Besides this, spin orbital MRAM uh, is also expected to have advantages in its scalability, retention, endurance, and power consumption. So before we go into the physics mechanism, I would like to introduce a little bit about the development of spintronic device. From 1990s to present, development of spintronics has experienced three stages. In the 1990s, the giant magnetoresistance and tunnel magnetoresistance lead to the new generation of magnetic storage. So in the TMR and GMR, the resistance will be different for parallel and anti-parallel states, but they are caused by different physics mechanisms. One is spin-dependent scattering, and another is tunneling. And at the beginning of 21st century, the semiconductor spintronics produced by the combination of spin and semiconductors became the research frontier. And it's recently that the research hotspots of spintronics have focused on concepts such as spin transfer torque effect, spin Hall effect, and the spin orbit torque effect. It is until 2019 that the current assist magnetization switching by the spin orbit torques was first observed in the ferromagnetic semiconductor. Then we come to the physics principles. The first one is the spin Hall effect. It is a transport phenomenon. When a current goes through a ferromagnetic material, the opposing surface boundaries will have spins of opposite sign. So in classic Hall effects, the charges of opposite sign accumulate on boundaries. It is similar to the spin Hall effect. So the relation between the spin current and the charge current is given in the first equation, where the theta SH is the spin Hall angle and sigma is the polarization. This equation shows the relation between the spin current density and the charge current density. So in the right picture, we can see that there are two kinds of torques. The first one is the damping-like torque, and the second one is the field-like torque. It has been predicted that the spin Hall effect will mainly induce damping-like torque in spin orbit torque. Also, experiments shows that the damping-like torque is predominant in this system. And it is later pointed out that the spin Hall effect can also produce field-like torque. So there are two mechanisms that will cause the spin Hall effect. The first one is spin orbit coupled scattering, and the second one is spin-dependent distortion of electrons' trajectory. So then another effect is the rushbar effect. It can be subdivided into interfacial rushbar effect and the bulk rushbar effect. And it is mainly caused by the space inversion symmetry broken. Two mechanisms can break the space inversion symmetry broken: the bulk inversion asymmetry, which is the BIA, and the structure inversion asymmetries, which is the SIA. So we mainly talk about the interfacial rushbar effect. It exists in the multi-layer for spin orbit torque research. So we can see in the top right picture that at the interface of two different materials, there's an electric field normal to the interface. And the field that generated is H equals alpha R Z cross K. Z is a unit vector parallel to the electric field E, and K is average electron wave vector. And alpha R is the material parameter that depends on the strength of the spin orbit coupling. So then we go to structure and mechanism of spin orbit torque MRAM. The basic structure for a spin orbit torque MRAM is also a three-layer MTJ. So the direction of the magnetic moment in free layer can be switched, which can be either parallel or anti-parallel to the fixed layer. And the electric resistance will be different. So typically, the low resistance state is considered to be 1, and the high resistance state means 0. The main difference between spin orbit torque and spin transfer torque MRAM is that the way of writing. The spin orbit torque MRAM base cell uses two separate injection lines for read and for write operations. So which means the write current does not go through the MTJ. The reading and the writing paths are separate from each other and can be controlled independently. So as is shown in this picture, the write current goes through the write path. It is usually a heavy metal conductor. And because of the combined effect of the spin Hall effect and the Rashba effect we mentioned before, the electrons of different polarizations will accumulate on different sides and thus generate a spin current flowing to the magnetic layer and induce spin orbit torque to switch the magnetic moment. So after we constructed the spin orbit torque MRAM, we need to evaluate its performance. So we need a framework which allows us to explore the spin orbit torque MRAM for various memory areas and its feasibility for caches. So a device level evaluation is conducted for a single base cell, and a circuit level analysis is performed for a complete memory area. And finally, it's the system level, which can both be a single core evaluation or a multi-core evaluation. So first, let's start from the circuit level performance. We give out the conclusion that in these circumstances, SRAM is a better choice in this small scale because the base cell for SRAM is larger and the peripheral circuitry is smaller. So, but as the scale of the memory goes larger, things will change because for small memory size, the peripheral circuitry dominates. And as a result, spin orbit torque MRAM costs more area. But as soon as the base cell area dominates the total area and not the peripheral circuitry, spin orbit torque MRAM provides smaller area. Also due to the same reason, the interconnection delays are less important in spin orbit torque MRAM memories. And consequently, the access latencies do not increase as the case for SRAM when increasing the memory size. As interconnection also influence the per access energy, spin orbit torque MRAM also offers a lower per access energy than SRAM for a larger memory size. So then is the system level performance. So the IM FlexCom is the in-memory flexible computing platform, which uses novel spin orbit torque MRAM area architecture. So showing this picture is an example of comparison between different kinds of memories. So the IM FlexCom memory shows the least write dynamic energy due to its low write voltage in comparison to other devices. It also greatly reduced the total leakage power compared to SRAM. It's able to improve the write latency up to 82% compared to standard spin transfer torque MRAM. And both, we can see from the table that both the MRAM design have shown longer write latencies compared to SRAM due to the longer write latency of magnetic memory storage device. And moreover, the area overhead of the proposed IM FlexCom memory model is 30% more than DRAM and STT-RAM, but 30% less than SRAM. So I need to mention one more point about spin orbit torque MRAM performance. So we showed it in this experiment that the resulting energy is significantly lower for spin orbit torque MRAM comparing with SRAM. The L2 cage is a kind of SRAM. Also, there's a disadvantage and challenge for spin orbit torque MRAM. The first one is about integration with CMOS. CMOS is technology used for constructing integrated circuit chips. So when integrating the spin orbit torque MTJ with CMOS, there will be an extra spin orbit couple layer compared with traditional spin transfer torque MTJ. So because of this unique device structure, spin orbit torque MTJ bears special process integration and control challenges in dimension, thickness, and the smoothness of heavy metal. And also, we need to correspond the thermal stability with spin Hall angle and conductivity. So this requires special engineering techniques in electronodes, film stacks, alignment accuracy, etching process, clean technology. So there's another disadvantage about density. We have mentioned before that the area for spin orbit torque MRAM is smaller than SRAM but bigger than spin transfer torque MRAM. So in order to further reduce area, researchers have developed a kind of called multi-level cell spin orbit torque MRAM. So it is shown in figure C and figure D. In figure C, it is called the parallel multi-level cell spin orbit torque MRAM. So the two MTJs have different critical currents. So then we can apply time-dependent or current-dependent writing. So in the time-dependent writing, so first a constant write current flows through the hard metal, and both the MTJ are programmed. And then we applied a current with short time duration, and only the fast MTJ, the MTJ2 will be programmed. There's another approach in figure D. It is called the series multi-level spin orbit torque MRAM. So the first is an MTJ in contact with heavy metal electron node. It can be programmed by spin orbit torque effect. But another one is the spin transfer torque MRAM. So this structure saves the area, but it needs a higher voltage because we need to switch the spin transfer torque MRAM. So for summaries, we've introduced the spin Hall effect and the Rashba effect, which cause spin orbit torque. But the distinction between these two kinds of effects is difficult because they mix together in the material. And for the evaluation performance, we need to consider different skills: the circuit, the device skills, and the system skills. In circuit level, the SRAM overall performance is better. But in system level, spin orbit torque MRAM is better because it has low energy consumption. And also the limitation we mentioned before is mostly the integration and the density. And it has some future opportunities for like 3D MRAM and spin optronics in exotic magnetic materials. So it is a powerful tool to manipulate magnetic dynamics and switch the uniform magnetization. And the spin orbit torque MRAM has the potential in the magnetic data storage and the high frequency magnetic device area. Okay, thank you.
Thanks so much. I think it's nice to compare it to SRAM, and I appreciate you looking at the density as well. Any questions for Jingyu? I can start out. Can you clarify what was the benefit there at the end of combining the SOT and STT? I thought the main benefit of SOT is being able to write not through the tunnel barrier, but then you still have to go through the tunnel barrier there. And D here. What was the benefit of D?
In this picture, the scientists tried to further reduce the area because I mentioned before in this.
But I guess why not just go to STT then? I understand that reduces the area, but then what benefit are you left with using SOT there?
It is maybe it saves the energy because for spin orbit torque it has the less energy compared with spin transfer torque. But
the switching energy, switching energy, you think?
Yeah.
Okay, maybe I'd look into it more. Any other questions?
So usually I've seen SOT MRAM with a 2T 1R structure, kind of like an A or C or D. But for B, so I think usually I see the 2T 1R structure because there's lots of sneak paths for SOT in circuit form. So for B, I guess what's the advantage of B, and why do I see less of it?
Actually here A and B is used to compare with C and D, and it is the basic spin orbit torque MRAM structure. So actually we want to introduce the advantage of C and D, which is a high density. There's no advantage for A and B. It is just a basic spin orbit torque MRAM structure here.
If I was to guess, BE was them considering the diode there is like a selector. So instead of having a 2T, you have a selector and a 1T. So like, yeah, as just, I know Samir knew this, but for everyone else, you know, a lot of things like RAM use selectors so that they could get away with not having a transistor resistor structure, which is huge area overhead. Yeah, whenever you talk to people from like, yeah, like our ECE colloquium speaker last week, Dan Werledge or others, why don't MRAM use selectors? They say it's because one of the big benefits of MRAM is endurance, and all of the selectors so far are very low endurance, more similar to RAM. So if anyone can do research on a really high endurance selector, like a high endurance diode, that would be really exciting for MRAM.